Good evening, everyone. So today in this session, we'll be discussing about the refraction of light. We'll be discussing about the refraction formula and lens makers formula as well, right? So we'll be starting with the concept of refraction, right? The refraction of light is actually the phenomena of bending of ray of light, and it passes obliquely from one medium to another medium, right? So bending of light, when a ray of light passes from one medium to another medium, and both the medium should have a different refractive index, right? And let's suppose you can see here the ray of light is passing from the air, right? The ray of light is passing from air. Let's suppose the first medium is air, and the second medium, it can be water or it can be any other medium, glass as well, right? When this ray of light will pass through the interface between the two mediums, right? Then this ray of light will bend, right? There will be bending of ray of light, and this bending of ray of light we call it as refraction, right? This is called as phenomena of refraction, right? So the refraction, in case of refraction, the ray of light can bend either towards the normal, right? You can see here, this is the interface, right? At point P, this is the interface. At point P, the ray of light strikes the interface between the two medium, and it's bending, right? Either towards the normal or away from the normal, right? Now we can see here if the frequency, velocity, and wavelength of light in the medium air is f, v1, and lambda 1, right? So when this ray of light passes through the medium second, then in the second medium, let's suppose this is the water, right? In this medium, the speed of the light is going to change, right? The speed of the light change. The wavelength of the light will also change, but the thing that will remain constant is the frequency of light, right? The frequency of light does not change upon changing the medium, right? It only depends upon the source of light. The frequency of light will be independent of the medium. It will only depend upon the source of the medium, right? So upon bending of light from one medium to another medium, the frequency of the light remains constant. Only the wavelength and the speed of a light change, right? Why the speed of light changes, right? Or we can say why the bending of the light takes place, right? This phenomena will be actually explained using the Huygens principle in the VedaEdutech chapter, right? So actually, we cannot explain it here. We'll be explaining this in the Huygens principle, right? Why the bending actually takes place, right? Even if the light slows down or the light slows down from one medium to another medium, why the bending takes place. This will be explained in the chapter wavelengths, right? So frequency of the light does not change upon changing the medium, right? Only the velocity or wavelength changes, right? So there are certain laws on which the refraction takes place, right? The laws of the reflection in the same manner, the refraction also follows some certain laws, right? And one of the law is that instant ray, refracted ray, and normal always will lie in the same plane, right? They will lie in the same plane. The instant ray of light, the refracted ray of light, and the normal will always lie in the same plane, right? They will not be out of plane, they will be in the same plane. This is the first law of refraction, right? And the second law of refraction is what this is also called as Snell's law, right? This is also called as Snell's law of refraction, right? The second law of refraction says that you can see here this is the incident ray of light. This is the incident ray, and the angle of incidence with the normal is I. And this ray of light bends towards the normal, right? With the angle of refraction equal to R, right? Angle of refraction equal to R. And the wavelength of this light is lambda 1 in medium 1 and lambda 2 in the medium 2, right? Then the second law of refraction says that sine of angle of incidence, ratio of sine of angle of incidence, right? It says that the ratio of sine of angle of incidence and sine of angle of refraction, right? It's always a constant, right? It's a constant. It means that if the angle of incidence is I, it means sine of I upon sine of R, it's a constant, right? It's a constant. It's a constant. And this constant here, we call it as a refractive index, right? Or relative refractive index. So this constant is nothing, it's the refractive index, right? So the refractive index actually gives us idea about the optical density of a medium, right? Or it gives us an idea about how slow or how fast the light is going to travel in a medium, right? So we can replace this constant with refractive index mu, right? And this refractive index gives us idea about the optical density, right? It gives us idea about the optical density of a medium, right? Means that how slow or the how fast a ray of light is going to move in a medium, right? It's not that of a, it's very different from that of normal density, right? So it's not comparable to the normal density, right? So normal density is defined as the mass per unit volume, right? But this is optical density. It gives us the idea about the speed of light in different mediums, right? So this ratio will always be constant between the two mediums at which the refraction takes place, right? This is what we call as Snell's law, right? These two laws will be followed at every interface where the refraction takes place, right? Now let's discuss more about the refractive index. There are two types of refractive indices. One we call as absolute refractive index, another we call as relative refractive index, right? So absolute refractive index is the refractive index of a medium as compared to the vacuum, right? Or we define it as the ratio of the speed of light in a vacuum to the speed of light in that medium. So absolute refractive index will be defined as speed of light in medium, let's speed of light in vacuum, that's C, and the speed of light in medium, right? Where V is nothing, it's the speed of light in medium. So this refractive index we call as speed of light in medium. This refractive index we call it as absolute refractive index, right? So it's a refractive index as compared to the speed of light in vacuum, right? Then we have the relative refractive index. So relative refractive index is the comparison between the refractive indices of the two different mediums, right? Where both the two mediums are different, not the vacuum, right? So when light passes from one medium to another medium, then refractive index of second medium with respect to the first medium, we call it as relative refractive index, right? Relative refractive index. So the relative refractive index is represented by mu2 upon mu1. It means if the refractive index of the second medium is mu2 and the refractive index of the first medium is mu1, we will write it as relative refractive index mu2 upon mu1, or in short we write it as mu21, right? So this is the relative refractive index. Either we write it as mu2 upon mu1 or mu21. It means that is the refractive index of second medium with respect to the first medium, and similarly the refractive index of first medium with respect to second medium can be written as mu12, right? That will be mu1 upon mu2, right? So this is what we call as the relative refractive index, right? This is called as the relative refractive index. Now we know that the relative refractive index is nothing that's equal to mu to 1, right? That's equal to mu 2 upon mu 1, right? Mu 2 upon mu 1, right? That will be equal to sine of angle of incidence upon sine of angle of refraction, right? That is sine I upon sine R. That's the relative refractive index, right? Now, we know the speed of light is nothing. Speed of light is equal to frequency times the wavelength, right? Frequency times the wavelength, right? And we know that this frequency remains constant between two different mediums. The only thing that changes is the velocity and the wavelength of a light, right? Now, let's suppose there are two different mediums. In first medium, the speed of light is v1, and in the second medium, the speed of light is v2. Then we can write here v1 will be equal to frequency times lambda 1, right? And the v2 will be equal to frequency times the lambda 2, right? Frequency times the lambda 2, right? Or from here, v1 upon v2 will be equal to lambda 1 upon lambda 2, right? Lambda 1 upon lambda 2. And we know mu2 will be defined as absolute refractive index of the second medium will be defined as C upon v2. And the absolute refractive index of first medium will be defined as C upon v1, right? C upon v1. Now we can see here, we can also write, we can see here uh, v2 upon C will be equal to mu2, right? It will be 1 upon mu2, and V1 upon C, it will be equal to 1 upon mu1, right? 1 upon mu1. Now, if we divide these two quantities, right, it will be V2 upon V1, right? It will be V2 upon V1. That will be equal to mu1 upon mu2, right? Mu1 upon mu, right? Or V1 upon V2, V1 upon V2 will be equal to mu2 upon mu1, right? Mu2 upon mu1. That means we can write this sine of angle of incidence sin I upon sin R also equal to V1 upon V2, right? V1 upon V2. That's sin I upon sin R, right? And V1 upon V2 is nothing, that's equal to lambda 1 upon lambda 2, right? Lambda 1 upon lambda 2. And that's equal to mu2 upon mu1, right? Mu2 upon mu1. So the relation between speed of light, Snell's law of wavelength, and the refractive index, we can write a complete relation between them, right? So the complete relation between them will be nothing. It will be sine of I upon sine of R. That will be equal to V1 upon V2, right? That will be equal to lambda 1 upon lambda 2, right? That will be equal to mu2 upon mu1, right? So we can use any equations, right, from this. From here, we can use any relation to find out the required quantity, right? So sine I upon sine R will be equal to V1 upon V2, right? That will be equal to lambda 1 upon lambda 2. That will be equal to mu2 upon mu1, right? Or we can write lambda 1 mu1 will be equal to lambda 2 mu2. So this is the relation between the wavelength and the refractive index, right? Absolute refractive index between different mediums, right? Now, let's talk about the bending of light ray. How the bending will take place, whether the bending will be towards the normal or it will be away from the normal, right? Now, let's suppose if the ray of light, according to Snell's law, sine I upon sine R, right? That's equal to mu2 upon mu1, right? Mu2 upon mu, right? Now, if the ray of light is coming from the rarer medium into the denser medium, then it's going to bend towards the normal according to the Snell's law, right? It will bend towards the normal, right? And similarly, if ray of light is coming from the denser medium to the rarer medium, entering into the rarer medium, then it's going to bend away from the normal, right? You can see here, it's bending towards the normal here in this case, towards normal. And here it will bend away from the normal. So it will bend away from the normal, right? Now let's try to solve a question on refractive index. A light ray incident on a glass surface of refractive index equal to 2, right? From here at an angle of incidence 45 degree, right? We have to find the angle of refraction and angle of deviation, right? So let's suppose this is the, let's suppose this is the interface between the two mediums, right? And this is the ray of light incident on a glass medium from here, right? And this is the normal, right? And this ray of light is going to bend towards the normal, right? It will be bent towards the normal. And the refractive index that's of air mu1 is equal to 1 and mu2 is a glass that is of refractive index equal to 2, right? Now angle of incidence is given as 45 degree. It means this angle is 45 degree, right? We have to find angle of refraction. That will be, we will be using Snell's law mu2 upon mu1. That will be equal to sine I upon sine, right? Sine I upon sine R. So mu2 is nothing, that's 2, mu1 is 1, right? And sine I is 45, right? That's sine 45 upon sine R. That is equal to 2, right? Or from here we can write sine R will be equal to sine 45 upon 2, right? That will be 1 upon 2 root 2, right? 1 upon 2 root. So that will be 1 upon 2 root 2. So sine of R or R will be equal to sine inverse of 1 upon 2 root 2, right? So it will be sine inverse of 1 upon 2 root 2. Now talking about the angle of deviation, right? So this was the original path of this ray of light. This was the original path of the ray of light. And this complete angle here will be the angle of incidence, right? So the angle of deviation, this much angle here will be the deviation from the original path, right? The angle of deviation here will be nothing. It will be I minus R. So that's the deviation, right? So I is 45 degree, right? And it will be sine inverse of 1 upon 2 root 2. So this will be the deviation in the incident ray of light. Now let's discuss total internal reflection. It's another phenomena with respect to the refraction, right? Let's discuss it. So what actually the total internal reflection is, we'll discuss it one by one. Let's suppose this is the case first here, right? This is the case first. And in this case, the ray of light is coming from the denser medium, right? In the part A, the ray of light is coming from the denser medium and is perpendicular to the interface, or we can say the angle of incidence is equal to 0, right? If the angle of incidence is equal to 0, angle of refraction has to be 0, right? According to Snell's law. So it will pass undeviated, right? It will pass undeviated, or we can say there will be no refraction at all, right? There will be no refraction. Angle of refraction will also be equal to 0, right? Let's suppose in the case second. Now let's suppose in the case second where incidenting this ray of light from the denser medium to the rarer medium at some angle of incidence I, right? At some angle of incidence I. Now this ray of light will bend away from the normal. You can see this ray of light will bend away from the normal, right? Or the angle of refraction will be greater as compared to the angle of incidence, right? Now the case third is, now if we increase this angle of incidence, and the angle of incidence will always, angle of refraction will be always greater than the angle of incidence, right? It means when the ray of light is coming from the denser medium into the rarer medium, it means that if we increase the angle of incidence from the denser medium, when the ray of light is coming from denser and entering to the rarer, if we increase the angle of incidence, then angle of refraction will increase continuously, right? So there will be a particular angle at which this refracted ray will just graze the interface, right? It will just graze the interface. So this angle at which the refracted ray will graze the interface and will try to come back into the same medium, this angle we call as critical angle, right? We call as critical angle. Now, if we further increase in the case D, you can see if we further increase the angle of incidence, then angle of refraction has to be greater than the angle of incidence, right? So it means that this refracted ray will not be now grazing the interface. It will actually come back to the same medium, right? It will come back into the same medium, or we can say it will be reflected back into the same medium. And this type of reflection, we call it as total internal reflection, right? So we can get a reflection, right, between the two mediums, right, without even polishing the surfaces, right? Even if the two mediums are transparent mediums, right, we can still have the reflection of the ray of light by the concept of this total internal reflection. It will depend upon the angle of incidence. If the ray of light is coming from the denser medium and entering into the rarer medium, right? You can see here, this is the normal here. This is the normal n, and after, if we further increase the angle of incidence greater than the critical angle, right, theta c, then angle of incidence, angle of refraction will further increase, right? Or we can say the ray will be totally reflected back into the same medium, right? So this is what we call as the total internal reflection, right? Total internal reflection. So after critical angle, the reflection will take place for the incident ray of light from denser medium to the rarer medium, right? Now let's try to find out what this critical angle is, how much this critical angle will be for different mediums, right? We can still apply the same law, that's the Snell's law, that's sine I upon sine R, that will be equal to mu 2 upon mu 1, right? Now here in this case, since the ray of light is coming from denser to the rarer, so the mu 2 here will be rarer medium and mu 1 has to be denser medium, right? So at this case, the angle of refraction will be 90 degree, R will be equal to 90 degree, right? Or from here, angle of incidence will be critical angle of incidence, sine NT will be equal to 1, it will be equal to mu 2 upon mu 1, right? Mu 2 upon mu 1. Now, if the real medium is air, right? If mu2 is equal to 1, for example, the real medium is air, right? In that case, the critical angle sine of theta c will be equal to 1 upon mu, where mu will be the refractive index of denser medium only. And from here, we can calculate the critical value of angle. That will be sine inverse of 1 upon mu, right? So this angle we call as critical angle, right? So after critical angle, so critical angle is the angle at which if we further increase the angle beyond the critical angle, the total internal reflection will take place, right? So ray of light will be totally reflected back, right, into the same medium, right? That's what we call as TIR. Now, one of the best applications of TIR is optical fibers, right? So we use optical fibers in our different communication systems, right? In our daily lives, we use the optical fibers for the communication or the transportation of the signals, right? So it also works on the same concept of TIR, total internal reflection, right? So there, the incident signal or the input signal is incident at some angle, right? And that angle is greater than the critical angle. Or we can say that incident signal does not actually leave this optical fiber. It gets totally internally reflected continuously, and it passes from one point to the another point, or we can say it passes from source to the receiver, right? So this is the important concept or the important application of the TIR which we use in our optical fibers, right? Now let's talk about the refraction through a prism, right? Let's talk about the refraction through a prism. So you can see here the refraction of prism. Let's suppose this is the incident ray of light which is incident at an angle of incident I, right? At an angle of incidence I, and this will be refracted according to the Snell's law, right? This angle will be the refraction angle, and this is the normal, right? This is the normal here. This is the angle of refraction. So R1 will be the first angle of refraction, right? And this ray of light will strike again onto the second face of this prism, right? And once again the refraction will take place, right? And it will bend once again, right? Now in this case, if the first medium is rarer medium, right, and the second medium is denser medium, right? So this ray of light will bend away from the normal, right? And there will be certain deviation in this emerging ray, right? So the light ray finally emerging out of this prism, we call it as emergent ray, and the angle at which it emerges from the normal, we call it as angle of emergence, right? So E is nothing here, E is the angle of emergence, right? E is nothing, it's the angle of emergence. So E is the angle of emergence here, right? Delta will be the net deviation, right? Net deviation is the delta here. This is the net deviation from the original path, because original path is this. This is the original path, and this is the final path. So the net deviation here is delta, right? So the delta will be the total deviation because of the first refraction and the second refraction, right? Or we can say delta will be nothing. It will be equal to delta 1 plus delta 2, right? That will be equal to delta 1 plus delta 2, right? Now you can see here, if this angle is R1, right, then this total angle here has to be equal to 90 minus R1, right? And if this angle is R2, then this total angle will be once again equal to 90 minus R2, right? And we know in case of triangle, the sum of all the interior angles is 180-degree, right? So it means A plus 90 minus R1 plus 90 minus R2 has to be equal to 180-degree, right? 180-degree, right? So from here 180, 90, 90 will get cancelled, or from here we can get the value of A equal to R1 plus R2. So this angle A, we call it as angle of prism. This is nothing, this is angle of prism. So angle of prism is actually the angle between the two surfaces or two planes at which the refraction through the prism takes place, right? So refraction takes place between this surface, right? This surface, surface 1, and between this surface 2. The angle between these two surfaces will be called as angle of prism, right? And it is equal to R1 plus R2. That's the angle of refractions, right? R1 here will be the angle of refraction for the first interface, and R2 will be here the angle of incidence for the second interface, right? So R1 plus R2 will be equal to A, right? Now let's talk about the net deviation, right? Net deviation. Now the net deviation here will be, if this is angle I, right? If this is the angle I, and this has to be angle I, right? It means the deviation first, delta deviation, delta 1 will be equal to I minus R1, right? I minus R1. And the second deviation will be equal to delta 2, right? That will be equal to E minus R2, right? E minus R2. That will be equal to E minus R2. This will be the second deviation, right? The total deviation will be delta 1 plus delta 2 for this prism. Total deviation will be delta 1 plus delta 2. That will be equal to I minus R1 plus E minus R2, right? Or we can write it equal to I plus E minus R1 plus R2, right? R1 plus R2. So this will be the total deviation, right? In this prism, I plus E minus R1 plus R2. R1 plus R2 here is equal to A. We can write it equal to A, right? So I plus E minus A is the total deviation in this for this light, incident ray of light on prism, right? Now let's see if we plot deviation versus the angle of incidence, right? Deviation versus the angle of incidence graph, right? You can see here it behaves like a parabolic curve, right? It behaves like a parabolic curve, right? Now this is the deviation, right? This is the deviation versus the angle of incidence, right? You can see here for two different angle of incidences there is same deviation, right? For two angle of incidences there is same deviation, right? If we join these 2 points here, these 2 points, the angle of incidence is I1 and the angle of incidence is I2, but for both these angle of incidences the deviation is same, right? The deviation is same, right? And you can see here there's a minima in this curve, right? This is the minimum value, right? And this minimum value of the deviation occurs at angle of incidence. This minimum deviation occurs at angle of incidence I equal to E. It means the deviation will be minimum at the point where angle of incidence will be equal to the angle of emergence, right? When the deviation is minimum, the angle of incidence is equal to angle of emergence, right? So delta will be equal to I plus E, right? I plus E minus A, right? Now in this case, at minimum deviation, I is equal to E, or we can write delta will be equal to 2 times I minus A, right? 2 times I minus A. So this will be the minimum deviation here, right? This will be the minimum deviation. Now, now applying the Snell's law at this condition, right? We'll apply the Snell's law for this condition. Sine of angle of incidence, right? Sine of angle of incidence upon sine of angle of refraction. That's equal to mu 2 upon mu 1, right? Mu 2 upon mu 1. Now when I is equal to E, right? I is equal to E. In that case, R1 will be equal to R2. That will be equal to A upon 2, right? It will be equal to A upon 2, right? It will be equal to A upon 2. So in that case, at minimum deviation, the angle of refractions will be equal to A upon 2 each, right? A upon 2 each. Now using R1 equal to A by 2, right? Using R1 equal to A by 2, right? And R2 also equal to A by 2, we'll get the value of refractive index, relative refractive index, that's mu 2 upon mu 1. That will be sine of A plus delta minimum, right? Upon 2, right? Divided by sine of A upon 2. So this will be the refractive index. this will be the refractive index for the minimum deviation, right? If mu1 is equal to 1, right? If mu1 is equal to 1, then this equation will be refractive index of this prism will be equal to sine of A plus delta M upon 2 divided by sine of A by 2, right? Sine of A by 2. Sine of A by 2, right? So this will be the condition for the minimum deviation, and this is how we can calculate the refractive index of prism using the condition of minimum deviation, right? Now let's discuss the refraction through curved surfaces, right? You can see here in this diagram we have a curved surface, right? We'll be deriving a formula for the refraction through the curved surface, right? And we'll be using the same formula to derive the focal length of a lens, or we can say lens maker's formula or lens formula, right? Now you can see here we have incident ray of light which is incident at point n, right? Which is incident at point n, and there is certain angle of refraction, right? That's equal to r, right? Angle of refraction is equal to r. Now you can see that this ray of light will meet at some point I on this axis, right? At some point I, this point will be called as image point, right? This point is called as image point. This point is called as image point, right? This point will be called as image point. Now we can apply the Snell's law at this condition. It means that mu2 upon mu1 will be equal to sine of angle of incidence, right? Sine of angle of incidence upon sine of angle of refraction, right? Sine of angle of refraction. That's mu2 upon mu1. Now, still we'll be using the same approximation here. The approximation is the parallax approximation. It means that the incident ray of light will be very close to the principal axis, right? Let's suppose this is the principal axis, right? This is the principal axis. We'll be using the parallax approximation that all these angles will be very small, or these rays of light will be very close to the principal axis, right? They will be very close to this principal axis, such that all these angles will be very small, so that we can use the approximation sine I will be equal to I and sine R will be approximated to R, right? So using parallax approximation, right? So using again the parallax approximation here. So I upon R will be nothing. That will be equal to mu2 upon mu1, right? Mu2 upon mu1. That will be equal to mu2 upon mu1, right? Now you can see in this triangle O and M, right? In this triangle O and M, right? Or in the triangle O and C, right? Triangle O and C. Triangle O and C. In triangle O and C, alpha and beta are the two opposite angles, and I is the exterior angle, right? I is the exterior angle. So we can write I equal to alpha plus beta, right? And similarly in the triangle NIC, beta is the exterior angle, right? We can write beta here equal to R plus gamma, right? R plus gamma. So from here, beta equal to R plus gamma, or R will be equal to beta minus gamma, right? Beta minus gamma. So R will be equal to beta minus gamma, correct? Now, alpha plus beta upon beta minus gamma, right? Beta minus gamma. That will be equal to mu2 upon mu1, right? Or we can write it equal to mu1 times alpha plus beta. That will be equal to mu2 times beta minus gamma, right? Beta minus gamma. Now, once again, we can use these parallax approximations, right? Using the parallax approximation, we'll calculate this angle alpha, beta, and gamma, right? You can see in this triangle O and M, in this triangle O, N, and M, this is a right angle triangle, right angled at M, right? We can use tan of alpha. So the tan of alpha here will be equal to tan of alpha here will be equal to Nm upon OM, right? nm upon om, right? And similarly, tan of beta will be equal to nm upon mc, right? Nm upon mc. It will be nm upon mc. Now tan of gamma from this triangle nmi, it will be nm upon mi, right? Nm upon mi. Now the distance from point M to this image point is called as the image distance, right? And the distance of this object from this point M, right, will be called as object distance, right? So OM will be equal to object distance, right? And IM will be equal to image distance, and MC here will be the radius of this curved surface, or we'll call it as radius of curvature, right? It will be the radius of curvature for this curved surface, right? Now substituting all these values, right, using the partial approximation, tan of alpha will tend to alpha, or alpha will be equal to nm upon om, right? And beta will be equal to nm upon mc, and gamma will be equal to nm upon mi, right? So this is the partial approximation, right? So finally we have mu1 alpha. Alpha is nm upon om plus beta, that is nm upon mc, and we have mu2, that's equal to beta, that's nm upon mc, minus gamma. Gamma is nm upon mi, right? Now from here nm is nothing. Nm will be cancelled out, right? Nm and nm will get cancelled, right, on the both sides. Now om is here. Om is nothing. Om is the object distance. We can write om as u, right? Can write om as u. So mu1 upon 1 upon u, right? And mc will be written here as equal to r, right? Plus 1 upon r, that's equal to mu2. The value of mc is, once again, we have mc here, right? So beta was equal to tan of beta is nm upon mc, right? And we have, so mu1 times beta, right? Okay, beta is nm upon mc, right? Nm upon mc. So mc here is nothing, is the radius of curvature, right? So 1 upon r, and we'll be left with minus 1 upon mi. Mi is the nothing, it's equal to the image distance, that's equal to v here, right? Image distance v. So it will be minus 1 upon v, right? Minus 1 upon v. Now what we'll do is that we'll rearrange them, right, to calculate the refraction formula, right? So it will be mu1 upon u plus mu1 upon r, that will be equal to mu2 upon r minus mu2 upon v, right? Mu2 upon v. So it will be mu1 upon u minus plus mu2 upon v, right? That will be equal to mu2 minus mu1 upon r, right? mu2 minus mu1 upon r. Now you can see here, taking the sign convention, the radius of curvature for this spherical surface here is along the direction of the incident ray of light. So r will be taken as positive, right? So r will be taken here as plus r, right? R will be taken here as plus r. But the object distance here will be taken as negative, it will be taken as minus u, and the image distance once again will be taken as positive, it will be plus v, right? So finally we have the equation, the final equation for the refraction formula here will be that is mu2 upon v minus mu1 upon u, right? That will be equal to mu2 minus mu1 upon r, right? So this formula we call as a refraction formula at the covered surface, right? So at any covered surface, we'll be using this formula to calculate the image distance, object distance, right, or the radius of curvature for the surface, right? So mu2 upon v minus mu1 upon U will be equal to mu2 minus mu1 upon R, right? So this will be the refraction formula, right? Now the same refraction formula can be used at this lens also, right? You know the lens is a portion of a transparent material with two refracting surfaces such that at least one surface is curved, right? And the refractive index of this material should be different from that of surrounding, right? That's the important condition for any material to be a lens, right? So you can see here we have a convex lens here, right? It's a convex lens here, right? It has two radius of curvature, one R1, another R2, right? Then we have equiconvex lens. So for equiconvex lens, we have the radius of curvature, both radius of curvature same, right? R and R, right? For equiconvex lens, the both radius of curvature will be equal to both will be equal, right? Now we'll be deriving the same formula, right? We'll be deriving the focal length for this lens. We know uh, the power of lens is nothing. It's the ability of a lens to bend the ray of light, right? Either towards the either towards the principal axis or away from the principal axis, right? Or we can say either it converges the ray of light, incident ray of light, or it diverges the ray of light. So the lens which converges the ray of light is called as convex lens, right? And the concave lens diverges the incident ray of light. Now we'll be applying the same refraction formula to calculate the lens maker's formula, and that formula is used to calculate the focal length of a lens, right? And we'll be deriving the mirror lens formula or lens equation from the same formula as well, right? Now we can see here there are two radii of curvature, right? R1 and R2, right? So there are two surfaces in this lens. It means that refraction will take place twice, right? Refraction will take place twice, right? Now let's apply the refraction formula, that's mu2 upon V minus mu1 upon U, right? That will be equal to mu2 minus mu1 upon R, right? We'll be using refraction formula one by one at both the surfaces, right? At both the surfaces, we'll be using this formula, right? Now let's apply this refraction formula at the surface one, right? At first surface, right? Now for the first surface, the curvature, radius of curvature is R1, right? And this radius of curvature, uh, at this radius of curvature, refraction will take place, right? And now let's suppose the image is formed at a distance of V1 from the optical center of this lens, right? So we can write mu2 upon V1, right? Mu2 upon V1 minus mu1 upon U, right? That will be equal to mu2 minus mu1 upon R1, right? Upon R1. Now let's call this equation as equation first, right? Similarly, for the second case, or we can say that at the second surface, the refraction will once again take place, right? But in this case, the second medium will be the mu1 and the first medium will be the mu2, right? But for the second surface, the object here will be the image formed because of the first refraction, right? So V1 will be the object distance for the second refraction, right? V1 will be the object distance for the second refraction. And let's suppose finally the image is formed at a distance of V. The final image is formed at a distance of V from the optical center of this lens, right? So V1 will be the object distance for the second surface, right? And the final image will be formed at distance V from the optical center, right? The second condition is mu2 here is it will be mu1, right? And the image is finally formed at a distance of V, right? And the mu1 here is the lens, and the lens is the refractive index mu2, right? Mu2, right? So it will be mu2 upon the object distance. The object distance is the image formed because of the first refraction. That's V1, right? V1. That will be equal to mu2 upon that will be mu1 minus mu2 upon R2, right? So this will be the second equation, right? Now what we'll be doing is that if we add these two equations, right? Add first and second, adding equation first and equation second, right? What we'll get is that so mu2 upon v1 and minus mu2 upon v1 it will get cancelled. We'll be left with mu1 upon v, right? Minus mu1 upon u, right? That will be equal to mu2 minus mu1 upon r1, right? Plus mu1 minus mu2 upon r2, right? R2. So from here, what we can do is that we can just take mu2 minus mu1 as common, right? Mu2 minus mu1 as common. So it will be left in the bracket as 1 upon R1 minus 1 upon R2, right? So from here, we'll be left with the final equation 1 upon V minus 1 upon U. mu1 will be taken as common, right? We'll be having mu2 minus mu1, right, as common once again. So it will be 1 upon R1 minus 1 upon R2. The final equation will be, final equation is 1 upon V minus 1 upon U, right, multiplied by mu1, that is equal to mu2 minus mu1, right, multiplied by 1 upon R1 minus 1 upon R2, right? Or we can write it as 1 upon V minus 1 upon U, that will be equal to mu2 minus mu1, right, upon mu1, right? That's equal to multiplied by 1 upon R1 minus 1 upon R2, right? So this is nothing. This is what we call as refraction formula, right? This is nothing. This will be the refraction formula for the lens, right? Refraction for lens. Now let's calculate the focal length from this equation. Now we know that focus is a point where the parallel beam of light rays actually converge after reflection or refraction, right? So it means that the object will be at infinity, right? Object will be at infinity, right? So object with distance will be infinity. 1 upon infinity will be equal to 0, and the image will be formed at focus, right? At the focus. So 1 upon f will be nothing. That will be equal to 1 upon f will be equal to mu2 minus mu1, right? Upon mu1 multiplied by 1 upon r1 minus 1 upon r2. So this equation we call it as lens maker's formula, right? Lens maker's formula. So with the help of this equation, we can calculate the focal length of a lens, right? This is the lens maker's formula, right? If this is the 1 upon f, then it means that we can write 1 upon v minus 1 upon 1 upon u equal to 1 upon f, right? So this is nothing. This is the lens formula, right? This is nothing. This is the lens formula. So from the same equation, we developed the both formulas or both the equations. One is the lens formula, another is the lens maker's formula to calculate the focal length of a lens, right? This is the lens formula, right? So both these equations are important to calculate different parameters of a lens, right? And the power of a lens is defined. Power of a lens is nothing. It's defined as 1 upon the focal length, right? 1 upon the focal length. Once the focal length is calculated using lens maker's formula, right, we can calculate the power of a lens, right? Or we can write power of a lens P equal to mu2 upon mu1 minus 1 multiplied by 1 upon r1 minus 1 upon r2. So this is the power of a lens, right? So in this way we can calculate the focal length of different lenses, right? So we used refraction formula, and the refraction formula can be used at any refracting surface, right? Curved surface, to calculate different parameters, right? So that is it for today, right? We'll be discussing wave optics in the next lecture, right? We'll be starting with the Huygens principle and then interference and diffraction, right? We'll stop here. See you in the next lecture.